Welcome to lecture number 34. Today we will start with the restricted three body problem. Already we have discussed about the general properties of the three body problems, and we know that from our previous discussion three body problem cannot be solved. So, in certain restricted cases its a solution can be worked out. So, therefore, we are trying to discuss about this restricted three body problem. That is why this notion comes, restricted three body problem. Now, the assumptions will make that the primary and the secondary bodies move in circular orbits about their center of mass. Okay. So, we have one mass here and another mass here. Okay. So, this we will call as m1 and m2, and the third body it is a lying say here, its mass is written as m. So, primary and the secondary body move in circular orbits. This is the assumption about their center of mass. So, center of mass may be lying here in this place. Okay. So, about the center of mass, the primary and the secondary bodies they are moving, okay, and that too in the circular orbit. So, this will make a circle like this here about the center of mass. Similarly, this will make a circle about the center of mass, and they will be moving such that they are always opposite to each other. So, this is the first assumption. The second assumption, the third body is very small as compared to the primary and the secondary bodies. So, say this is the primary and this is the secondary body. So, third body which is located here, this is very small as compared to the primary and the secondary. Say in the case of the, I have here earth, and this point I have moon, and I have a satellite here. So, we know that satellite can be of few thousand kgs. Okay. So, while the earth and moon they are very massive as compared to the satellite. So, in no way, though there is obviously gravitational attraction between all of them, but the satellite gravitational attraction on the earth will be feeble, okay, and therefore, it can be neglected altogether. So, therefore, the second assumption we make, the third body is very small, so that it does not affect the primary and the secondary bodies. Additionally, we can have one more constraint, okay, but it is not necessary. The third constraint which I am showing here. So, this is written here, the third one. The third body may be considered to move in the orbital plane, of the primary and the secondary bodies. So, in that case you are assuming that the motion is planar, but it is not necessary. This is an additional constraint that you can implement, otherwise it is not required. So, with this with these two assumptions we start our work, and let us draw the figure first, and thereafter we will. So, we have here two bodies. This will show as the primary and this as the secondary. Somewhere the center of mass is located here, which will indicate by B, and B is nothing but the barycenter. In this case we call the barycenter. This will write as m1, and this is point A, and this we write as no, then B we cannot write the other one. Let us make this as okay, B is okay for this place, we will make it C, A, B and C. This mass will indicate by m2. This let us consider m1 is the primary, mass. It does not matter, you can assume m2 also to be the primary, and M2 is the secondary mass. Okay. Now, we have to fix a reference frame here in this place. So, let us say we put a reference frame. First, we define one synodic reference frame. So, synodic reference frame, I am just putting this blue line here, which is indicating the synodic reference frame axis. This is axis is in the x direction of synodic frame. There is difference between the synodic frame and the barycentric frame, as I will explain you. But remember that reference frame and the coordinate frame, the difference already perhaps I have explained. The reference frame, in the reference frame we write the equation of motion, there the Newton's law is applicable, but not in the coordinate frame. Coordinate frame is used to describe the position of the particle, or it may be whatever, okay. But there you cannot write the equation of motion. So, reference frame especially refers to the frame in which we are defining the motion. So, here in this case this is the x s direction, and then in this direction we show y s, and z s will be vertically up. Therefore, x s, y s, z s, this constitutes the synodic frame. Already I have stated that A and C, the mass m1 and m2, mass m1 and m2 are moving in circular orbit about their center of mass B. Synodic frame is located at synodic frame origin, basically here in this case this is the origin, it is located at B, but the synodic frame is rotating. Synodic frame is rotating such that, or so that, axis always points towards M1. So, here in this case what is the effect that so, the effect is that the angular velocity of the synodic frame and the masses m1 and m2 are the same as a result of this, and this is written as omega s. So, omega s, this is the angular velocity Ct of the synodic frame. Now, barycenter also we need to define, and arbitrarily we can do that. Let us say that barycenter, I show it along this direction, this is x b, then y b can be here in this direction, and similarly z b we can show in this direction, okay, and it is located at B. Okay. It is located at B. I have separated it out here. the actually the barycenter and the point for the synodic origin of the synodic frame, which is here, they will coincide, but for the sake that it is a visible, I have drawn it separately, little separation I have maintained. Otherwise, they are the same. This is your synodic frame. So, your barycentric frame, it is shown like this. It will overlap with this. So, this is your synodic frame x b, y b and z b, and similarly here x s, y s and z s. Y s and z s, and x b, y b, z b. And it is not necessary that both of them this z b direction is the same, it can be different. I can choose any direction, I can also take it like this using the right hand rule. Okay, so, with this description, now we are set to start the formulation of the equation, but for our formulation I will remove this x b y b so that the figure looks neat and clean. Okay. So, we do it on the next page. M 1, M 2 and then we have this is x b, y b and z b. Satellite is located somewhere here. Okay, so, coordinate of this one we can indicate like this, drop a perpendicular in the plane of the mass, plane of the orbit of the masses m 1 and m 2, and thereafter we drop perpendicular on this one like this. Okay. We can see that how the coordinates then will be defined. And then the we write this as r. R is the radius vector or the position vector of mass m. Little more change I will do to make it more clear, because the axis I have to draw. This is mass m. Now, if we extend y x axis here in this direction, obviously in this direction we will have the axis. So, this is your maybe we have written x s y s, this is the synodic frame we have written, and x b y b already I have shown on the previous page, which we are, this is the barycentric frame, the related to barycentric and this is related to synodic. And this point we write as O. So, what we observe from this place, that the components are this component, because it is lying along the x axis. So, we can write this as x, this becomes y, and this component is z, and this is your vector from this place to this place, which is the radius vector. This is your r. So, purposefully we have removed the barycentric frame. You can write also the equation of motion in the barycentric frame, but we are going to represent in terms of the synodic reference frame components, and reason for that will be very soon visible to you. So, x s, y s, z s already stated that these are indicating the synodic frame. And this point we have written as B earlier. So, we will write this as the B we have represented as the barycenter. Okay, so, for writing the equation of motion, we need to find the forces acting on this mass. Mass is located here, we have the mass here in this point. So, we need to find what are the forces acting on this. Then we draw the radius vector from m 1 to this to the mass m, and we write this as r 1. Similarly, we draw the radius vector this is r 2. Okay. So, m times d square r by dt square the equation of motion always will first write in the equation of motion will be written in barycentric frame which is inertial. And now, what are the forces acting on this? This we have to write, and thereafter we will reduce it to the synodic frame. This is the process we are going to use. Now, the forces due to the mass m 1 and m 2 we have to calculate. So, therefore, due to the mass m 1 we will have the force acting on this particle will be given by this r 1 cube, and in which direction this force is acting? This is acting just opposite to the r 1 vector. So, we write here with a minus sign. Similarly, you can see that the forces acting force acting due to the mass m 2 on the mass m, okay. This is g times m 2 m divided by r 2 whole cube and r 2. In the barycentric frame. Remember that r 1 I can write this as say the component in the synodic frame, we can write it like this, where r 1 is the vector or one more step is required here. This part we will change little bit. Actually, what we can show here that r 1 is nothing but r minus x s, or say r minus the coordinate of mass coordinate of mass m1. And what is the coordinate of mass m1? If I indicate it by this is your r. So, r minus this quantity. So, and this part if we write as coordinate with respect to the barycentric frame. So, let us write this as a x b with respect to the b frame b to 1. Okay. As we have been indicating the notation we have been using. So, this is b located here and b to 1, in this point you have 1 mass m 1. So, it will go like this and the synodic frame direction, this is the way we will express it. Okay. Similarly, R 2 we can write as r minus. Now, here in this case you are taking positive direction of x along this direction. So, this will be negative 1. Okay. So, therefore, this can be written as x b 2, or if I put a plus sign and here this is the coordinate of I will explain you what does it mean if I write it like this minus E 1 cap. So, this one is E 1 cap I am taking here in this direction and E 2 cap along this direction, E 3 cap along this direction in the synodic frame. And this notation I am going to use. For the barycentric, you can put a symbol here in the upper one, like I can use a symbol E 1 b indicating that this is a unit vector along the x direction of the barycentric frame. Similarly, E cap b 2, it is a unit vector along the y direction of the barycentric frame, but this is not required. The part I am going to explain you, that will make you understand what I am trying to do here. So, if I write it this way, so this indicates this is the magnitude x b 2. X b 2 is the distance from this point to this point, okay, from b to m 2. This is your x b 2, and similarly, the distance from this point to this point, this is x b 1. So, this is the magnitude and multiplied by the vector along this direction. So, this vector is minus E 1 cap. Here in this direction, this is E 1 cap. Okay. And therefore, now this is consistent, this is minus sign here. You can see that for getting this vector, this r 1, I need to subtract from r the vector going from this place to this place up to the mass m 1. Okay, from here to this place to this place, as I am showing on the in the figure. Okay. So, this is done this way, the same way this is done, and you have to remember that here whatever is appearing, this is indicating the magnitude. Okay. If you do not want to write it in terms of magnitude, one more point here, you can see that this sign here is minus, here also this minus, but this minus sign here and this minus sign ultimately it will make it plus. So, this is the difference, and if you put then the particular value of the x b 1 and x b 2 in the magnitude. So, your r 1 and r 2 vector will be available to you. Otherwise, you do not also require putting it this way, you just keep it x b 2 here in this place, and here in this place, as I am showing by this arrow, you can put a plus sign. So, if you do that, then you have to put here for x b 2 while you are working the negative sign. Okay. So, these are the ways of doing, and various authors can do the same problem in multiple ways. This is the approach I am taking, because it will be convenient to represent it. Okay. Now, this I have shown in the synodic frame. If I write the same thing, one more thing you should note, that any vector r can be written in terms of the synodic reference frame. Let us say its components are x. So, x E 1 cap, y E 2 cap and z E 3 cap. So, this is in the synodic frame. The same vector if you describe in the barycentric frame. So, I will write this as the x b E 1 cap b, y b E 2 cap B and Z B E 3 cap B. So, this is indicating in the barycentric frame. So, components will change, but the vector r does not change. So, the components here just it is changing. So, based on this our whole analysis will depend. So, these two, if you use this, you will get the result in terms of the barycentric frame, and if you use this, then you get the results in terms of the synodic frame, but the treatment of the problem then will be little different for the barycentric frame. We have this equation written, the equation of motion first in the barycentric frame. This we have to do necessarily, there is no option to that, because we have to always write the Newton's law in an inertial reference frame. Now, we will reduce it to the synodic reference frame, which we have assumed it is a rotating with angular velocity omega s. So, this is the angular velocity of the synodic frame. And is nothing but also the angular velocity of the mass m 1 and m 2. Okay. So, with this basic formulation, now we can proceed and work out the whole problem. In the next step, m we can eliminate from this equation. So, this can be written as d square r by dt square equal to minus g m 1 by r 1 cube and this we brief as mu 1 by r 1 cube minus mu 2 by r 2 cube r 2, where mu 1 equal to g times m 1 and mu 2 equal to g times m 2. Thus, we have our equation in the inertial frame as mu 1 by r 1 cube equation of motion of mass m barycentric frame, and this can be reduced in terms of the synodic frame. For this, you need to look into this relationship. If this is in the barycentric frame, so dr by dt, this with respect to the synodic frame omega cross r. So, with this notation, so what this is indicating, that I have a inertial frame here, which I am writing as the barycentric frame. Another frame I have here, which I am writing as synodic frame. Omega is the angular velocity of this frame, and let us say, so what I am interested, that I have one point here located whose radius vector is r 1 or simply r. This is simply r, okay. So, rate of change of this r in the barycentric frame, if it is written like this, so it can be expressed in this way, and this is pretty simple. Let us do this quickly here in this place. R equal to, we express this in terms of the synodic frame components x s, or simply we will write x not to complicate the whole thing, E 1 cap y times E 2 cap plus z times E 3 cap. This is a vector given to us. If we differentiate this vector with respect to time in the barycentric frame, and then this the other things will be given as x times omega cross E 1 cap plus y times omega cross E 2 cap plus z times omega cross E 3 cap. So, here the vector r, this is the point P here. So, it may be moving, and because of this components are changing in the synodic frame. You first just differentiate this. Once you differentiate this part, while breaking this up and applying the normal calculus rule, so we can break here in this part. Okay. Once we have broken it like this part then becomes dx by or dr by dt with respect to the synodic frame. In the synodic frame, this is the synodic frame E 1, E 2 and E 3, these are the unit vectors located along. So, unit vector in the synodic frame does not change, it is a fixed, okay, and this frame itself is changing, it is a rotating. Okay. This frame right now it is a like this, after some time it may be looking like this. So, this is E 1, E 2, E 3, later on E 1, E 2 and E 3, it becomes like this. So, it rotates because of presence of this omega. So, this indicates your motion with respect to the synodic frame, and this part already I have discussed this part while discussing the central force motion. Differentiation of we are doing differentiation of d E 1 by dt, which is nothing but omega cross E 1 cap, and this we have discussed while discussing about the central force motion. So, I am no longer expanding that again, y E 2 cap times z E 3 cap. Therefore, this gets reduced to dr by dt with respect to the synodic frame and omega cross r. So, dr by dt with respect to the barycentric frame will be equal to dr by dt with respect to the synodic frame and plus omega cross r. Okay, so, we stop here and will continue in the next lecture. The same whatever we have left, we will complete that. Okay, thank you.